Good evening, sir. Good evening, classmates. I am John Grace Aralia, and today I will be discussing our solution for homework 2, problem number 7.
For our problem statement, let x upper 1 and x upper 2 be bivariate normal random variables, each representing the femur and humerus lengths of individuals in two communities. Assume that x upper 1 and x upper 2 have means mu upper 1 equal to mu 1 1, mu 1 2 prime, and mu upper 2 equal to mu 2 1, mu 2 2 prime respectively, and a common covariance matrix sigma. Samples of sizes n1 is equal to 27 and n sub 2 is equal to 20 yielded respective sample means x bar upper 1 equal to 460.4, 335.1 prime, and x bar upper 2 equal to 444.3, 323.1 prime, and 1 all over n sub 1 plus n sub 2 minus 2a equal to this matrix 561.8, 380.7, 380.7, and 343.2, where A is equal to the summation of x upper 1 alpha minus x bar upper 1 quantity x upper 1 alpha minus x bar upper 1 quantity prime, where alpha is equal to 1 to n sub 1, plus the summation of x upper 2 alpha minus x bar upper 2 quantity x upper 2 alpha minus x bar upper 2 prime, where alpha is equal to 1 to n sub 2. Consider testing the hypothesis H sub O, where mu upper 1 is equal to mu upper 2, and H sub 1 where mu upper 1 is not equal to mu upper 2, and the univariate hypothesis H sub 01, where mu 11 is equal to mu 21, and H11 where mu 11 is not equal to mu 21, and H sub 02 where mu 12 is equal to mu 22, and H12 where mu 12 is not equal to mu 22. Show that the test based on Hotelling's t-squared accepts H sub O at 5% level of significance, and yet students' t-test rejects both H sub 01 and H sub 02 at 5% level of significance. Explain what may have caused this apparent inconsistency. For our solution, we first define our hypothesis testing as follows based on testing two means with common covariance matrix H sub O, where mu upper 1 is equal to mu upper 2, equivalently mu upper 1 minus mu upper 2 equal to 0, and our alternative hypothesis mu upper 1 not equal to mu upper 2, equivalently mu upper 1 minus mu upper 2 not equal to 0. Recall that the pattern for t squared is given by t squared equal to normal vector prime multiplied to the inverse of the unbiased estimator of its covariance matrix multiplied by the normal vector. So to proceed with this, we first define the normal vector under H sub O to be x bar upper 1 minus x bar upper 2, where the distribution of x bar upper 1 minus x bar upper 2 is a normal multivariate normal distribution with mean mu upper 1 minus mu upper 2 and covariance 1 all over n sub 1 plus 1 over n sub 2 sigma, where mu upper 1 minus mu upper 2 is equal to 0 under H sub O. Second, we derive the middle term of t squared, which is the unbiased estimator of covariance matrix of our normal vector. Note that from the variance of the above distribution, sigma is a population parameter, and hence we need to derive its unbiased estimator. We note from our course notes that expectation of S is equal to sigma. Hence, from the above, the unbiased estimator for n sub 1 plus n sub 2 all over n1, n2 sigma is given by n sub 1 plus n sub 2 all over n1, n2 S. Building the t-squared, we have t-squared equal to x bar upper 1 minus x bar upper 2 prime quantity the inverse of n sub 1 plus n sub 2 all over n1 n2 as quantity x bar upper 1 minus x bar upper 2. And we have the result t squared is equal to 5.461261. Next, we derive the F statistics from page 43 with our alpha 0.05. Then we plug in the values from the above results and we have 2.66995. From the F table, our critical value is given by 3.209278. Based on the above results, our F statistic, which is 2.66995, is less than our critical value, which is 3.209278. Hence, we do not reject the null hypothesis. This means that there is no sufficient evidence that the means from the two communities are significantly different. Now, for the univariate hypothesis testing, our null hypothesis mu sub 1 1 is equal to mu sub 2 1. Equivalently, mu sub 1 1 minus mu sub 2 1 is equal to 0. And for our alternative hypothesis, mu sub 1 1 not equal to mu sub 2 1. Equivalently, mu sub 1 1 minus mu sub 2 1 not equal to 0. We note though that from our S matrix, we can quickly derive the pooled variance and we can now calculate for our T statistic. Using the formula for T statistic, we arrive at the result T is equal to 2.302412 and our critical value is given by 2.014103. From the above result, our T statistic 2.302412 is greater than our critical value 2.014103. Hence, we reject the null hypothesis. This means that there is sufficient evidence to say that the mean length of femur are significantly different between two communities. For our second univariate hypothesis, our null hypothesis mu sub 1 2 is equal to mu sub 2 2. Equivalently, mu sub 1 2 minus mu sub 2 2 is equal to 0. And our alternative hypothesis mu sub 1 2 is not equal to mu sub 2 2. Equivalently, mu sub 1 2 minus mu sub 2 2 not equal to 0. We note though that from our S matrix, we can quickly derive the pooled variance and we can now calculate for our T statistic. Using the formula for T statistic, we arrive at the result T is equal to 2.195612 and our critical value is given by 2.014103. And from the above result, our T statistic 2.195612 is greater than our T critical value 2.014103. Hence, we reject the null hypothesis. This means that there is sufficient evidence to say that the mean length of humerus are significantly different between two communities. And to answer the last question regarding the inconsistency of the acceptance or rejection, we would like to invoke the illustration from UNM math slides. So notice that the rejection region for T squared is the region outside the ellipse, while the one for the univariate is outside the rectangular area. So we can notice that it is still possible to accept the null hypothesis for T squared while we reject the univariate test. Its probability is defined by the area outside the rectangular region but within the ellipsoid region, which is exactly what happened in our problem. That ends my presentation. Thank you for listening and have a blessed evening.